Hey everyone, welcome back to my channel. In this episode we will learn how to solve numerically the radial Schrodinger equation for hydrogen atom using Numerov technique. We know from the basic quantum mechanics the radial part of the Schrodinger equation for hydrogen atom in atomic units, that means in where all the Pesky constants are set equals to 1. You can check any standard text on quantum mechanics, say Griffiths, and this is something like that. And here u is basically r times capital R into r is the radial wave function multiplied by r, L is the angular momentum quantum number, and E is the energy eigenvalue. And this equation can be casted as something like this: d2u dr2 minus, that is equals to m minus fr ur, and as there is no first order derivative in this equation, that means del u del r term, so it can be casted in Numerov method, and discretized form of the Numerov method is something like that. You can check any standard text or sources. Here h is the step size for radial coordinate, and fr, this function, is this object without minus sign. And in the atomic unit I have already said all the Pesky constants set equals to 1, say, and from the analytical calculation we know the energy eigenvalues are En equals to that is equals to minus 1 by 2n square. For ground state, 1s state rather, that means n equals to 1, the energy is minus half, that is 0.5 minus 0.5 in atomic unit. And for 2s state, that means n equals to 2, L equals to 0, and energy eigenvalues are this minus 1 by 8, that is minus 0.125 unit. These are the analytical results, and you can find it in any standard undergraduate quantum mechanics text. Now we going to discuss the implementation using Python 3. First we have to import some library for NumPy as for array, first array processing, and for plotting matplotlib.pyplot, and for root finding we are just calling the bisect function from scip.optimize module. Now we set L equals to 0, angular momentum quantum number is 0, r mean is 1 into 10 to the power minus 5, because we start very close to 0 in order to avoid singularity, because at r equals to 0 there is a singularity in this equation. So we start with some small value, and r max, say in this case 20, and we divide the whole thing in a grid. Number of grid points are 1000, and we create a array of points in R, that is np dot linspace r min to r max 1000 points, and it will return a array of array, in this case R, and it will return the return step true, that means h, that is the distance between 2 points will be h, that is the step size. And first we define the fr function in the Numerov method, that is 2 into e plus 2 into 2 by r minus L into this object. Now we define the Numerov driver, that is here Numerov method is implemented here. First we have declared a wave function with zeros, np dot zeros of array of n zeros, and u0, that means the boundary value is u0 is 0, and small initial value which is say u1, that is 1 into 10 to the power minus 5. Now we first pre-computes for a given energy and for a given value of r here. F values are calculated here. First we calculate this, and after that we run a loop from 1 to n minus 1. This is a standard Numerov formula. This formula is implemented here with computed f values. That means f values means, you know, from in this equation f is something like this. It is computed at once for a given value of energy and r, and it will return the complete wave function, that means u, from r equals to 0 to r equals to r max, not 0 but close to 0. Now another function is defined, psi at L, that means at other boundary we call the Numerov, that means for a given energy it will return the last value of the wave function, that means at the boundary at the r max, as we have discussed in the earlier episode, where I have discussed 1D box and harmonic oscillator problem. And here we defined an empty list U R max, and for energy range NP dot A range from minus 0.7 to 0 in the step of 001, these energy scan, and for E in this energy range from minus 0.7 to 0, we call the function psi at E, that means this function will return the last value of the wave function. Last value means at R max, what is the value of wave function at R max, that will be returned. And here we just create a array where for a different values of energy we just store the value of wave functions. We know for a particular value of energy E, for a set of values of energy rather, the wave function at R max will vanish. That is the basic of shooting method, as I have discussed in earlier episodes, 2 episodes. You can check that why this is important. And now we plot for E range and U max for a different energy range where U max vanishes. We can see visually, and these are the decoration part. I am not discussing this. Now I bisect. We know the energy, the ground state energy is within that is 0.5. That means I have to search 0.6 to 0.4. Before doing that, if you just run this program, here we see that means at energy value just like near to 0.5 minus 0.5, here is a cutting point, there is another cutting point, there is another cutting point, etc. That means the root is 0.6 within 0.6 to 0.4, and after seeing this graph you just set the bisect program E eigenvalue, that is bisect psi at L from minus 0.6 to minus 0.4, because the root is in between 0.6 and 0.4, and print the ground state energy. This is the ground state energy. And what is the normalized wave function? U equals to Numerov. We call the Numerov with E eigen or a given energy. It will return the complete wave function. And normalization, as we have discussed in earlier episode, this is as usual, and we plot the normalized ground state wave function, and this is the radial wave function for hydrogen atom, and this is this. And as you know, the found energy eigenvalues is minus 0.4999, that means almost 5. Exact value is 5, and there is a slight difference. You can calculate that. This is the ground state energy. This is the ground state wave function, that means norm square, and that is mod psi square, and if you plot without square, and it will be something like that. It is the plot of psi, and previous one is mod psi square. And in order to calculate this energy, that means it is between 0.2 to minus 0.1, minus 0.2, if you just set it minus 0.2 and minus 0.1, you run this, and this is something like that. This is 2A state basically, and if you know the squared mod psi square, that is probability density, it will be something like that. It is familiar to a state for hydrogen atom. This is a very elementary program for undergraduate students, and thank you for watching. If you have any questions, and you can comment, you can write in the comment section, and thank you for watching. And if you want to share, you can share.